Hi and welcome everyone. My name is Helen Rost and I will give a presentation about Airborne LiDAR strip adjustment using the TerraMatch software. So when do you do strip adjustment? Well, after data capture you calculate the point cloud, and as a part of the quality assurance process you do a strip adjustment to ensure good georeferencing and good geometric accuracy in the point cloud. And by assuring good quality, you can start to create products from the point cloud. So, why do you do strip adjustment? Well, you do it because you want to correct for remaining errors in georeferencing. Although GNSS and INS give you really good georeferencing, there are still some errors remaining that will, if you correct them, you will improve the quality of the point cloud. So you do it to minimize the mismatch between flight lines, and you do it because you want to minimize the offset towards ground control. There might also be some remaining errors from bore sight calibration of the system, so you do it to correct for remaining errors of bore sight. You also know that georeferencing will be improved by strip adjustment, and you want to ensure good quality before you do further processing. So at the bottom you see a typical point cloud that has a poor bore sight calibration, and after the strip adjustment you have a situation where the different flight lines match each other much better. The key features of TerraMatch is that it reads, stores and processes, first of all, LiDAR point clouds, of course, but also you need trajectories to process the data properly. And if you want to adjust to ground control points, you need to also have some ground control. The ground control could be points, lines, surfaces, or other point clouds. In TerraMatch you create observations, and you mainly create the observations in flight line or drive path overlap. And of course you also create observations of ground control objects. And then when you have the observations, you model and calculate corrections to trajectories. And when you have these corrections, you can apply them on, first of all, the point clouds, of course, but if you like, you can also apply the corrections on the actual trajectories. If you have simultaneous image capture, you might want to apply the corrections on image exterior orientations, and you could also apply the corrections on the observations made. So many of the routines in TerraMatch are automatic, and this is good for when you would like to process large data sets, but also semi-automatic and manual measurements are possible to do. TerraMatch also offers visual interpretation during the process. That means that the person who processes the data can make observations of the results during the process. TerraMatch also offers statistical output reports which will give you information about the geometric accuracy along the process. This means that the user can interact during the procedure, which creates better understanding what is happening and also a more robust result. It's not a black box where you just press a key and then you get the result. It's something that you can interact with during the procedure. I have a couple of examples. I will go through one. First of all, example 1 is an Airborne LiDAR area project, which is maybe the most common one. So I have a few short videos and I will give you, well, we go through each of these videos and look at the software. So the first part is an automatic search of observations in this area. So I can just tell you something about the area. It's about 30 times 15 kilometers. And here you have the Airborne LiDAR project with a number of LAS files, which corresponds to these squares in the design file. You also have the trajectories that are connected to the LiDAR points by time tags. The trajectories have line numbers 1, 2, 3, 4 and so on, and the lines are divided into groups, and each group in this case is different flight sessions. So this 149 is one flight session and 150 is another flight session. And I think there are 3 flight sessions in this area. To prepare data, I have made ground classification in the LiDAR point cloud, and the ground classification is done by doing a classification, individual classification for each flight line. This means that the ground surface can be compared between the flight lines and between overlapping flight lines. So you will have 2 ground surfaces in the overlap. And this means that you can compare these 2 lines or these 2 surfaces and get statistical output and observations of how well the flight lines fit. So I will start the Define Timeline tool in TerraMatch, where you give some settings and refer to the correct trajectories. And now I want to start the search of observations. So I will go to the automatic search timelines, and I will choose to look for surface lines, which means, and in slope direction, which means I try to find sloping surfaces and that will be used as observations. I will look for the observations in all the entire project, and I will look for with a density of 10 meters, meaning that you have 1 observation every 10 meters approximately. So just make sure that I have the correct project. and the correct setting, and I press OK, and it will start searching in the blocks. And when it has gone through all the blocks in the project, I will get a printout of the tilelines here in the design file. It found about 650,000 observations in this area. You can see we have two crossing flight lines at the start and the end, at the north and the south, and we have overlap between adjacent flight lines, parallel flight lines in the area. So I can see they are well spread over the area. There are some empty areas here, but they are excluded because that is water bodies, and water bodies are not to be included in the matching. So when you have made the automatic search, you would like to look at the result, display mismatches, and search for gross errors. So we will look at that video. So first of all, you can make an output report to get some statistics of the tilelines. And in here, for example, you can have statistics of the magnitude, RMS, maximum values in easting, northing, and elevation. This is for the entire project, and then you can also get statistics per flight line and also per group, which is flight session. So here you can see if there's any flight line or any group that stands out with a higher mismatch. In general, you have a mismatch with about 20 centimeters in XY and 7 centimeters in elevation in RMS, and the average mismatch is about 23 centimeters in XY and 5 centimeters in elevation. You could save that report, but I will just close it, and I will go to the display mode setting. If I would like to have some knowledge about how the errors are spread over the area, I could say that, okay, display only mismatches that are larger than 10 centimeters. I can see that they are all over the place. If I increase this value, I get fewer and fewer observations that are bad. And I can also see that the worst mismatch is in the center of the area where you have overlap between two flight sessions. You could also see what the slope is in the area by choosing slope display mode, and you can see that it's quite small slopes in this area. This is typical Sweden, rather flat terrain. Yep. I could do find worst. I usually do that to look at the worst mismatch in the area to see if it's a good or a bad observation, but in this case it looks quite natural. I can't say that anything is bad about this. I don't have enough information. So there's also you can choose to make gross error detection by deleting positions or timelines by criteria. So for example, you can, if you choose to delete all XY mismatch that is larger than a specific value, you can do that, but before you do it, you can also see the number of timelines that has a mismatch worse than 1 meter. So by choosing different numbers here, I can see how many observations will be deleted. So for elevation mismatch, I have to go down rather much, down to 30 centimeter to get any response here. So there are 9 tile lines that are larger, has larger mismatch than 30 centimeters, but smaller than 40. I won't do I won't delete any of the observations. There are a few that are quite large, but I don't know if that is because they are bad observations or if it's actually a mismatch from depending on bad georeferencing. I don't know yet, so I will keep all observations. I could also choose filter bad, which make like a smoothing curve, and it will take away all the observations that does not fit this curve. So the first step of the correction procedure will be to look for bore site errors. So I will do bore site calibration on this dataset, on these observations. So then I will go to timeline, find match, and I will choose to do bore site heading roll pitch correction, but I will do it on each group separately. This is because I want to know if there's any difference between the flight sessions. I will also include the elevation shift, because when you fly different days, for example, you have different GNSS satellite configurations, and this could generate an offset in elevation. So I will want to take care of that too. So I will also correct for individual heading roll pitch for each flight session. So this is, then I will model a combination of the actual bore site of the system and whatever shift you could have in the heading roll pitch depending on reinitialization of the inertial system. So this is a quite common way to treat these airborne projects, and you can see I would want to solve for each group separately. So here's the result. You can see that the XY mismatch went down from 7 centimeters to 4.5, and the elevation from 5.5 centimeters to 4 centimeters. And here you see the corrections, and you see that there's a shift in elevation, and from the first to the last flight session there's a shift of about 8 centimeters, so it's quite a lot. You see the heading roll pitch bore sight calibration offsets are quite similar, but there's a small difference between each flight session. So you could save this as a report if you like, but I would like to do only I want to save the result as a TerraMatch solution file. So these values you see here can be stored in a TMS file by doing save corrections. So this is the first set of corrections I want to do. I call it bore sight per day, as the flight sessions were 1 per day. So that is my bore sight calibration. And I can stop there. So the next step would be to do flight line corrections. And before doing the flight line correction, I want to apply the bore sight calibration. So on the loaded timelines I have here, I would like to apply the corrections found in the previous step, the bore sight calibration. Here you see the values, and they will be, the timelines will be corrected for these values. So now you can see that the mismatch in this timeline went from about 1 meter to about 70 centimeters. We can look at the output report. What was 23 and 5.5 centimeters X, Y, and Z mismatch is now about 15 and 4 centimeters. So it's a little bit smaller. So now I want to solve for individual corrections for each line. So instead of group, I choose individual lines, but I make the same heading, roll, pitch, and Z correction. I could also choose to do easting, northing, but in these airborne type of projects, easting and northing is very much correlated to roll and pitch errors, and so it wouldn't make much sense. You could have like large values as a result in both these that will they will take each other out. So instead of doing corrections for all, I will, as they are correlated, I will only use heading, roll, pitch shift, and elevation shift for each flight line. So this is the result. So we started with 15 centimeter XY mismatch, and now we're down to 4.5. And we started with about 4.5. No, we started with 4.5 mismatch in XY. Now we're down to 3 centimeters and about 2 centimeters in elevation. So I want to store these corrections as a TerraMatch solution file, which is called per flight line TMS. So now we have both bore sight calibration and strip adjustment flight line correction. And now we want to apply these on the actual LiDAR data. So for doing this efficiently, I will do a macro. So I will add the first step would be to apply corrections, and I will choose to do the bore sight correction first. as a first step, and then the next step would be to apply the corrections per flight line. I will save this macro. And I call it apply correction number 1. And I will do the correction of the LAS project, the LiDAR project. And I will make a copy of the data. I make sure I have the correct macro here. Correction number 1. Create a copy and save it to a folder that I call corrected. And now it will process all 84 blocks. So this is one of the blocks before the corrections. You can see to the right that you have some mismatch between the two flight lines. And now I open the corrected project and open the same block with the corrected data. And then you can see that there is no mismatch between the red and the green flight line to the right. So now I have a data set which has undergone internal calibration. You can say that you have a good situation in the overlap between flight lines, but you have no idea about how well it fits the control points. So now we will do an example of ground control point adjustment. So I will start the timeline observations, and I will choose to search for elevation control points. So I will import the points automatically and make an automatic observation collection, and I will choose to open all control points in the area in one step. So it will match the control point coordinates to the LiDAR points, and these are my observations. And you can see, even though it was about 160 points, they are placed in 4 different areas. So it's about 40 points in each of these 4 areas. You can see that the average mismatch is about 5 centimeters, and if I do a correction of plus 5 centimeters, 4 or 4.7 centimeters to the laser points, I will have much better match between the control points and the LiDAR points. So that is one way to do it, just to shift the LiDAR point cloud to make it fit better to the control points. Another way of doing it is to make like a rubber sheet fit. So I will go to the TerraMatch rubber sheet fit tool, and in this tool I can choose what kind of correction, X, Y, or Z I want to do. In this case, I would like to merge and average all points that are close by. So I say that any point within 100 meters at maximum 50 points, those I will use to merge as one correction. So ideally I will get 4 corrections, 1 at each of these 4 locations. So here's the result. I can see that the mismatch goes from 5 centimeters to 2.5. So these 2.5 centimeters represent the noise level in these observations, and the corrections in these 4 different locations are going from 2.5 centimeters to 6.5 centimeters. So it's a difference of 4 centimeters total internally in the area between these 4 locations. So one could choose to either do one shift of all data of 5 centimeters or choose to use this rubber sheet correction. So I could save also this correction as a TerraMatch solution file, so I can do save corrections. And I will call it rubber sheet elevation, rubber sheet set. To do the correction, I will make a new macro, and in this case I would do apply correction. I use the rubber sheet Z TerraMatch solution file, TMS file, and we call it apply correction number 2. Then I can make the correction on the LiDAR points. So I will run this macro on the corrected data. I will just improve this corrected data, and so I will choose write over original. So now we can have a look at the result. So we start by opening the original data and have a look at the output control report, which takes these elevation control points and make a statistical output. So in this output report of the control points, how well they match the original data, you can see that I have in total an average delta Z of minus 13 centimeters and a RMS value of 15 centimeters. So this is on the original data. So 13 and 15 centimeters you can keep in mind, and then I can open the corrected data set and make an output report on the control points. And here we see the result from output control report after the corrections on the LiDAR points, and you can see it has been a considerable improvement. We have an average offset near 0, and the RMS value is down to 3 centimeters. And one could save this report and put it in a larger context. So this was the control point adjustment. So now I want to show you an example of a corridor project. It's more or less the same procedure, but it could be that you have other types of observations. So here I want to show you an example of another type of observation procedure. So here we have a road, and we have control points which are actually on lines, so it's control lines. So you have known points that you know are at the center of this line. So it will give you a position of the road to the right and left, but not along the track. So now I have chosen this vector in the design file, and I can use that as to import known lines. So it's automatic line search. And I have the paint markings as a text file, XYZ text file, and now it has imported 87 lines. And you see the observations here. It has which flight line it has, which time stamp, mismatch in XY, and mismatch in elevation. So I should go through these observations to see if there are any strange if the automatic search has failed. So if I want to if I think this is a bad one, I could just enter a manual position, so I will measure the same painted line manually. So here I show you an example where I go through these observations, and when I think they have made a bad match, I will do a manual measurement. And of course, when you have sparse data, the automatic search fails more easily. When you have dense data with distinct intensity, then it is more successful. I could also do find worst. So by finding the worst, I can find the poorest or the largest mismatch, and I could enter the positions manually, or in this case I made a deletion because I deleted the observation because I thought the intensity value was not good enough to make a proper observation. So that is another way of going through the observations. So by doing these observations along the road, I can make another type of correction. This is fluctuating correction. So this is typical for corridor jobs, especially for structure like roads or railroads. And here I can choose to have different types of correction curves. So I can have a free curve, which means that I correct every line individually, and then interpolate to the next line or the next observation. I could have a restricted curve, which will have a smoothened correction, but it will be restricted to the accuracy of the trajectories. And you could have a smooth curve, which is smoothened with no restrictions, and the smoothing is made by doing Gaussian filtering. So in this case, I will choose a Gaussian curve, Gaussian smoothing, and I will do it in X, Y, and Z. And here's the result. You do see in the report, I went from about 10 centimeters to 1 centimeter final mismatch. And in these fluctuations, I can see the actual corrections to be made. And the red dots are the original measurements, and the blue lines are the corrections. So I can choose if I want to show the X, Y, or Z correction, or easting, northing elevation correction. I can also choose which range I want in the display. I can also choose which flight line to look at. Now I look at flight line 13, and now I look at flight line 7, and I can see how it fluctuates over time. Now I turn to Y correction. So the time goes from left to right. You can see the time tag at the top. When I'm done, I save the corrections to a TerraMatch solution file, a TMS file, and I will call it XYZ fluctuations. And I could apply these corrections both on data and on the timelines. So for example, if I apply it on the timelines, you can see that the mismatch between the timelines is much smaller, and the average and RMS values are much smaller. So to summarize, TerraMatch offers tools for improving georeferencing of LiDAR point clouds. Actually, you can process other type of point clouds, but you need trajectories. So it could be used for both airborne and mobile. Could be used also for personal laser scanning with the equipment that you carry on a person, either holding or attaching, but you still need trajectories. You should use different strategies depending on which type of project it is. If it's an area project, if it is a corridor project or SLAM project. The user can interact in the process, and it's possible to do visual and statistical evaluation along with the procedure and also of the result. So thank you very much for your attention, and I hope to see you again. Thank you.